Today's lesson is on linear algebra. So we're going to start linear algebra. We'll continue with that next time or the next few times. So we're going to spread this one out. This is definitely one of the areas that people said they needed, more practice on. So we'll do that. I want to start with just kind of a high level question though. Why do we study linear algebra at all as data scientists or data scientists in training? What does it do for us? Yeah, this is great. It's interesting. People really focused on one particular idea here, which is a little bit different from the direction I'm going to go with it, but it's a great point. Yeah, so I'll share what everyone said so we can talk about it together. But yeah, let's take a look at some of these answers. So this was the intent that was most consistently expressed. Basically, we have a lot of numbers, and linear algebra provides us with some conveniences for dealing with them. So instead of having to deal with 100,000 separate numbers, which conceptually gets to be a big mess, we can sort of package them together into a matrix or a vector or whatever sort of configuration of data is appropriate, and then think about that in our heads as one object, manipulate it in a program as one object. That has performance benefits. It has benefits for conceptual clarity. There are some other ideas here that I also want to riff on a little bit. So it provides an understanding for the structure of data sets. That's the direction we're going to go with this shortly. And we'll think about exactly what that means, at least sort of one particular facet of what it means. Provides a foundation for some machine learning algorithms. That's true. Linear regression is a really important machine learning algorithm or statistical method, depending on your perspective. But yeah, it gives us some direct tools as well as just general conceptual framework for doing lots of other kind of intermediate things we're going to want to do. And yeah, so this is a similar idea. We want to extract linear relationships between data sometimes, not always. Sometimes relationships will be more complex, but many data sets are sort of well handled by linear methods, and that's important. So yeah, really nice job kicking off with answers to that first question. So here's the answer that I want to give and run with in class today. Linear algebra provides us the conceptual and computational tools for understanding linear structure in high-dimensional data. So you'll spend the whole year learning how to extract all kinds of interesting structure from data, particularly high-dimensional data. But linear methods are specific to linear structure. And that's a really important kind of structure. We'll see some examples of that. But before we get into that, let's first talk about what high dimensional even means. So let's say we compile data on the number of atoms and the total weight for 10 million molecules. Would we say that this is a high dimensional data set or not? Great, so people are really on target with this one. Not a lot of folks have submitted yet, but I can see that people are definitely on the right track. Cool. So yeah, I'll summarize. Actually, let's hear from somebody. Tong, do you want to talk about what you see here? Great. So I'll share the examples of things that people said. So you can see folks are on point here. Yeah, when we talk about high dimensional data, the idea is that when we geometrically visualize a data set, the points in that space that we're visualizing are the rows of the data set. So that's the conventional way to lay out a data frame, so that your observations or your examples are in the rows. And as you move across from one column to the next, you're looking at different features, different facets of each example. So when we visualize a point, that vector or that collection of data that we're visualizing is coming from a particular row. This is a two-dimensional data set. What we would have is a ton of points, but just in the plane. And that's going to be much easier to think about in a lot of ways than a higher dimensional data set. But of course, in real life, you want a high dimensional data set, really, because that's giving you a lot of information to go on. You might, so, points in the plane might not separate themselves out very well, where you can really tell what's going on. But in higher dimensions, there's more space, and you can kind of do a better job. This is why, Facebook wants to collect a lot of data on how you use their site. Because if they have a ton of data, they can use that to make really sharp predictions about, what kind of ads you're going to respond to and so on. Okay, so yeah, anyway, bottom line, it's not a high dimensional data set. And incidentally, if you want to think more about this relationship between, like, let's say image data or some others kind of naturally high dimensional data and its representation in a high dimensional feature space, and kind of what that has to do with machine learning models and the way that we visualize things geometrically in low dimension. That is the subject of the ML with Mathlets mini course, which you can find linked from the prisme.chat page or that link right there. And it's supposed to be for a non-technical audience, so it doesn't take a long time to kind of work through it. It's got a bunch of interactive things. That's hopefully pretty fun. Let's move on now to thinking about what it means to talk about the structure of a data set, or rather the linear structure of a data set. So I want to kind of put a picture in your mind to kind of anchor you as we move forward, so you can kind of come back to this picture and think about it in the context of what we're going to discuss later. So if we have a data set like this one, the first thing that jumps out to your visual cortex here is that these points are really falling along a line. Almost. There's a little wiggle room. They're of course not exactly on a line, but roughly speaking, we're looking at points here which have some very clear linear structure. And we would really like to be able to grab that linear structure. We'd like to be able to take a list of all these coordinates. You can hover over a point and see its coordinates. So there's a bunch of data here, and we'd like to be able to somehow extract from those numbers a line that, just visually does what I'm doing with my mouse here, just kind of cuts along right through those points, right? That would be a helpful thing to do, because if we just see the numbers, like, this information isn't going to be apparent to us. It's only clear in the picture. And if we have a way of extracting that, we can easily distinguish this kind of structure from a data set like this one from one like this one, let's say, which is similar but with completely different line, or one like this one where there's really no linear structure and it's just kind of a cloud of points, versus one like this one where in some sense there's some linear structure, like the points have a natural order to them related to where they sit along this spiral. On the other hand, it's not flat, it's curvy, and this is going to be a different thing. This is going to require different methods to kind of discover this structure and do something useful with it from a data science perspective. And the other thing I want to say, because when people see points that lie along a line, conceptually what you probably do is snap to linear regression. You think, I know what to do. I'm going to find a line of best fit. And that's what we're talking about now. It's not. I want to talk about this more broadly than that. This is really just a plane collection of points in the plane, and we want to understand something like, what sort of line is it sitting alongside? Or is it sitting naturally sort of along some line? And so, maybe the vertical coordinate does represent a variable we're trying to predict, and the horizontal coordinate represents a feature or a value that we're using to predict the y coordinate. In that case, that would be a linear regression problem, or it would be a regression problem, and linear regression would be a very natural choice. But maybe what we're trying to do is predict a categorical variable, which is not shown in the figure, but could be in the data set. And so there's a symmetry between the X and Y axis. It's not you're predicting one from the other. They're both things that you have, and you're trying to predict some other thing. But it's still going to be useful to know that the points lie along a line. We can probably simplify our model, kind of maybe avoid some pathologies that we might run into if we're not recognizing, like, hey, these points actually fall along a line. If we treated it more like a point cloud or something, we might get into some trouble, or some things might not work as well. The point is, you want to know stuff. If you see these orange points, clearly your brain immediately tells you, like, first thing you want to know is they lie along this line. Linear algebra is going to equip us to do this in situations where we can't consult our visual cortex. So we'll usually have more than 2 features or more than 3 features, and we won't be able to just plot it and be like, oh, this is secretly a 5-dimensional data set, even though it looks 15-dimensional or whatever. We'll have to have some techniques that allow us to do this thing that your eyeballs do automatically when they look at this particular collection of orange points right here. And one thing I want to say, because it's something that I think can make people feel a little inferior. We start talking about high-dimensional spaces, and they're like, okay, I can visualize a plane, I can visualize 3-dimensional space because that's what I live in. But these people who can visualize 4-dimensional space or 10-dimensional space or 10,000-dimensional space, they really must be operating on a totally different cognitive plane. And I want to say that is the wrong idea. The 2D and 3D pictures are giving us geometric intuition that we can sort of take lessons from and apply it to higher dimensional data. But we really have to think about dimensions beyond 3 in a way that doesn't really use geometric intuition directly. We have to sort of develop a toolkit for mapping ideas back and forth between the geometric space, which is low dimensional and which we have good intuition for, and these higher dimensional spaces. So this connection, we really have to lean on these two things, which is just analogy, which doesn't support a lot of weight, but can be useful for intuition. And then also by concrete mathematical ideas that establish some correspondence between something algebraic that we can apply in any dimension and something geometric that we can think about in low dimensions in both ways. Okay, so just to make this point a little more concrete. So look at this data set. So I'm giving you a table here, which has 10 columns and 100 rows, and I'm putting all the numbers just right there like a spreadsheet for you to look at. And so this is, I could have presented this data for this data set in the same way. I could have just given you there'd be 2 columns and I forgot how many points are here, 40 rows or something. And I could have asked, like, do these points lie along a line? And you'd have been like, I don't know. You could start doing some computation to try to figure it out, but just glancing at them, you really wouldn't be able to tell much. And that's even more true here because there's just way too many numbers. It's not surprising that this is not a useful way for us to reason about questions like, is this data secretly lower dimensional than it really looks? So in fact, because of how I generated these data, so this is just fake data, I just made it up, but I did it in such a way that all of these points actually sit pretty close to a particular 3-dimensional space. So, in the same way that the line is kind of carving out a slice in the plane, these data really kind of carve out a 3D space sitting inside of the 10-dimensional space that each point sort of naturally sits in. And what we're going to build towards is a way of figuring that out, a way of computing with these numbers in such a way that it kind of jumps out at us in some way that turns out to be very mathematically elegant and intuitively satisfying, because it's kind of bringing together geometry and computation in a really cool way. And it's going to jump out at us like, oh, this is really pretty much a 3-dimensional data set with a little bit of noise, in the same way that the orange points we saw above lie quite close to a particular line. And, for better or worse, I like it. I think it kind of justifies this journey we're going to take through all of these linear algebra ideas. But this particular piece of mathematical insight that drives what we're going to do to extract this information about how the sort of linear structure of these points in the sense that we've described, it's not easy. It's not something we can just set up and do right now. We have to walk through a lot of linear algebra ideas, kind of get some things really down pat, and then we can start telling the story specifically of how to look at a data set and tell sort of in what sense is it well represented by a lower dimensional data set. So there's going to be a lot of moving parts there, and we're going to have to warm up to it. It's really what we're going to get to at the very end. So I just kind of want to see quickly how people are thinking about the thing that I just said. So what does it mean to say that the points in that data set above sit very close to a 3D space? So geometrically, it's clear in 2 dimensions sitting along a line what we're talking about. You don't necessarily want to leave it at geometric intuition when we're talking about high dimensions, though, because we don't really have geometric intuition for that. So what does it mean concretely to say that this data set up here looks like the points are 10-dimensional, but secretly they're really kind of just 3-dimensional plus a little bit of noise? Yeah, so what's sneaky about this? So like a lot of people are saying something like, well, a lot of the coordinates are close to 0. And well, that's not true directly, because if you just look across at these points, like you don't see any columns that are dominated by zeros. All these numbers are sort of, 2 or 1, or, there's very few tiny numbers. But it's still true in spirit, because the idea is like if you change your perspective somehow, and instead of just looking directly at the original columns, you look at some other, combination of columns in some way, and you kind of shuffle this data set around somehow, then you're going to start to see columns of zeros showing up, or numbers that are really close to 0 that can be essentially ignored. And that's one way to think about it. I'll just say something more basic that doesn't tap into any kind of more advanced machinery that we haven't gotten to yet, which is that what it means is that there are 3 vectors in R10. So there are 3 vectors we could write down as sort of, another row looking like these rows here, in such a way that each one of these rows could be written as a linear combination of those 3 rows approximately. It would be close, it wouldn't be exact, but it would be quite close. And here I've just, if you haven't done linear algebra before, I've introduced a new piece of terminology. If you have, hopefully you know this, but either way, I want to check in with you about it. So what does, I accidentally made the correct answer in the open response a suggestion chip instead of, keeping it behind the scenes. Yeah, so maybe we should just move on. I didn't get any utility out of kind of seeing where people are on that. Okay, but that's fine. We'll recoup some of that time. So a linear combination of a list of vectors is an expression that's obtained by scaling each vector in the list by some factor and then summing the results. So I want to jump straight to the geometric picture here. So, this gray vector and this gray vector are being added. One of the first one plus one of the second one gives this particular teal vector here with the orange head. And the reason we have this orange head is that you can scale the vector by adjusting this slider and it will show you all the points that the head ends up at. So if we scale how much of this particular gray vector that we're taking, then we get all of these points, and then we can adjust this one a little bit. We see that kind of moves us in another direction, specifically the direction of this gray vector. And then we can kind of switch it up and see how this is what it means to form a linear combination of these 2 gray vectors. We just choose any 2, they're called weights or coefficients, C1 and C2 that we want. And we can just like slide them around, and this point just moves around freely in the plane. So that's kind of the mental model I want you to have when you think about linear combinations. So these 2 operations that we're talking about here, so scaling, adjusting the number in front of the vector that makes it sort of longer or shorter and flips its direction, and summing vectors where we, just take a step represented by this vector followed by a step represented by this vector and see where we end up. So that is the sum here is represented by this teal vector. These are the fundamental operations of linear algebra. So in fact, when you do linear algebra from a pure mathematical point of view, you'll define what's called an abstract vector space. And the idea is, forget this concrete representation of a vector as an arrow in the plane. We want to talk about any objects that do this stuff. They do scaling and adding. So you can add any 2 of them together. You can scale any of them by a factor. And that's all you assume in a pure mathematical abstract vector space. And so that really points to the idea that summing and scaling vectors are really the 2 fundamental operations that we're going to build everything else out of to some extent. We will deviate from that a little bit later when we talk about vectors being at a right angle with respect to one another. That is an important idea, and it doesn't flow from just summing and scaling. But this is really, summing and scaling really are the 2 most important things. So if you didn't know that content before, then it's a lot. We're going to break it down. We're going to kind of start back from the beginning, but I wanted to sort of lay out a preview of where we're headed with this so that you can get some appreciation for the connection between data science and linear algebra. Because otherwise at the beginning, it can seem a little dry, like, why are we learning this? But it really comes together very beautifully at the end. I want to ask you to be patient with the linear algebra course, because there's a lot of stuff early on that's maybe not super scintillating, but towards the end, everything comes together really fast, and you get a lot of amazing ideas kind of one after the other. So hang in there for that. Okay, so let's talk about vectors. So roughly speaking, the term linear in mathematics, I mean, there are many ways you could describe it. This is one you haven't heard before. I want to say that linear means flat stuff. So for example, lines and planes are flat geometric objects, and they are geometric models for some of the most important ideas in in linear algebra, which is vector spaces. To just quote a different example, linear transformations are functions from one space to another. So I'll say this word pretty often, Euclidean space. I just mean like R1, the number line, R2, the plane, R3, 3D space or R4, R5, or so on, just one of those spaces. So linear transformation is a function from one Euclidean space to another, which maps equally spaced lines to equally spaced lines or perhaps points. So linear transformations are also flat. They're flat maps instead of flat geometric objects. But generally speaking, linear, you should think some sort of picture of flatness. So let's start with the very simplest flat thing, a line, and specifically just a line in the plane. So I won't even draw it. Imagine a plane with a line in it. There are lots of ways to describe a line in the plane that you have learned in previous schooling. For example, maybe the first thing you learned, or certainly very early on, you learned about slope and intercept. You can describe a line on a plane in terms of its slope and where it hits the y-axis. You could also, alternatively, although we don't do it as often, we could talk about the angle that a given line makes with the horizontal direction. So that's just going to have a direct connection with the slope. But there's another way to do it that we tend to use less in grade school when we talk about lines, but it's also worth thinking about. Or I guess we do talk about this when we talk about slope, but we don't really characterize it as a way to describe the line. So we'll see, you'll see what I mean in a minute. So the idea is, like, if we have a line, we can just draw an arrow that runs along the line. And that seems kind of wasteful, like we already had the line. What's the point of drawing an arrow on it? But the point is that you can then describe that arrow with numbers by saying, like, how far right did you have to move and how far up did you have to move in going from the tail or beginning of that arrow to the head or end of that arrow. So what's one significant disadvantage of describing a line in these terms? So you don't do this in grade school because it's not perfect. There's some drawbacks. So what's the disadvantage of describing a line in terms of the X and Y values of some arrow, or we're going to call this green thing a vector that runs along the line? Okay, so yeah, so folks had lots of ideas. Here's kind of the main one, and then here's another kind of related one. Yeah, this is another good way to say it. So yeah, nice job here. So we don't know where on the Euclidean plane it begins and ends. That's exactly right. So if I just tell you how far right and up I move to go from the tail to the head, we don't know where along the line that arrow is situated. And we could also move things, up and down. We don't know where in the plane it's situated. So this is an incomplete way to specify a line. That's for sure. So, and there's more slack than that, because, like, how long does the arrow need to be? You can draw an arrow within a line of a lot of different lengths. And, is one really better than the other? There's also the fact that it can be pointing in the opposite direction. So we're kind of, in choosing an arrow, we're sort of choosing an orientation for the line, which is not part of the line, really. So, these are all meaningful drawbacks, because, like, if you do y equals mx plus b, then m and b are uniquely determined by the line. So everybody's going to get the same answer. And there's not as much sort of, wishy-washiness involved. On the other hand, what's the significant advantage of describing a line in terms of the coordinates of an arrow that run along it? So let me just summarize what folks are saying, and then I'll just go ahead and share my answer. Okay, so here's one advantage. So this is turning the disadvantage on its head into an advantage. So we can use the arrow that we situate on the line to parameterize the line. In other words, we can anchor it somewhere on the line, and then it basically sort of sets up one coordinate axis for us along that line. So for example, if we describe this line that goes through this big blue vector, in terms of the blue vector, then we know that this vector is 4/5 of this one. And so that gives us a kind of, a one number name for this point, a way to describe where it is in terms of a single number. The 0 point is down here, the 1 point is up here. And so you can imagine like a number line that's just sitting along the direction of this line that's got tick marks on it with, 0 here, 1 here, 2, and so on. And then the negatives go this way. So that's kind of nice. It allows us to talk about where points are on the line in a really kind of flexible, useful way. So that's called parameterizing the line. And that's great. That's a definite advantage of using this particular approach. Another one, which also explains why y equals mx plus b is more favored when you're first learning about linear systems and so on. the concept of angle doesn't work so well when you go up in dimension. So like, an angle of a line in the plane is fine. You just measure this angle right here. It's going to be, whatever it is, it's a single number, and it tells us that the sort of, direction of the line. That's fine. But in 3D space, if you've done, if you ever worked with phi and theta, or if not, then think about the globe, latitude and longitude. Those are angular measures needed to specify direction in 3D space, and they're complicated. They're not the same as each other. Longitude goes all the way around the circle, whereas latitude only goes sort of, minus pi to pi, like due north to due south. If you thought about this, there's some complexity there. And the complexity really grows as you go up in dimension. So you just really don't want to be thinking in terms of angles when you're in high dimensions. You want to be able to just say, okay, here's a vector that runs in this direction, like take a step in the direction of that vector, and that'll keep you on the line. That's a much better situation, this kind of parametric description that we just looked at. Another advantage, which again is not really a factor early on, but as we move into higher dimensions, it becomes important, is that if the space that you're trying to parameterize is higher dimensional, so instead of just a line, let's say you're trying to describe a plane, this method works really nicely. We can grab, instead of one vector, we grab two vectors that lie along the shape that we're trying to describe, in this case, a plane. And then we can, let both of those vary freely in length, and we'll sweep out, the sum of those two will sweep out the plane. So there's kind of a natural generalization where you just throw in an extra vector and we get planes. So, and then we can kind of move up from there. So it generalizes very nicely. It's not kind of tied to low dimensions in a way that something like y equals mx plus b is. So here's a question to kind of break this up. So if we want to specify a plane in this way, where we grab two vectors on the plane and then look at all their linear combinations to sweep out the plane, what's the thing we need to make sure that we do in the process of grabbing these two vectors that we're going to use to try to represent this plane in this way? Yeah, so I'll share Imre's answer. Imre, do you want to explain this one to us? Yeah, exactly. So that's what's going on here. If we chose this orange vector and then we chose the green one to run in the same direction, we wouldn't actually be reaching all of these other points. So we need to make sure that the second one is not running in the same direction as the first one. Incidentally, several folks already said this, but in case you didn't, or if you did, just repeat it. What is the linear algebra term for this concept? This requirement that each vector needs to not represent the same directions that are already represented by the previous ones. Great. So people are on point with this one. Nice job. I'll share what everybody said. Yeah, so this is called linear independent. So a list of vectors is linearly independent if each vector in the list cannot be represented as a linear combination of the previous ones. This is a bit of an aside in some sense, but I want to draw attention to this because we're going to circle back to this later. It's going to be an important idea, and I want to kind of plant a seed in your mind for this now. So we can take vectors that run in nearly the same direction. But if vectors that run in exactly the same direction are kind of bad, ones that run nearly the same direction, maybe they're sort of bad too. And I want you to think a little bit about why that's the case. So you can play with this thing. I encourage you to move it slowly so that you get lots of trace points as you move it. These two gray vectors, they're nearly pointing the same direction, but not quite. So what's not great about that? Yeah, we have a couple of superb answers here. Nick, do you want to talk about your answer? Yes, we have to use larger weights if we want to reach faraway points. If you think about what it's going to take to reach a point like this, we can't do it with the constraints of the weights here. We have to have the sliders be much longer, kind of cover more terrain. Another way to say that is to sort of point out what a grid looks like. So if we look at the grid that we get here, so I did it in this bare bones way by having these orange points kind of trace out and be left as residue in the plane. And it looks kind of ugly. It's maybe a little hard to see what's going on here. This is going to be part of the point. We'll look at a better version of this in a minute. But just kind of to make this clear, if you have these points which are nearly parallel, it's really kind of scrunching up this grid on you. Like, who wants to do geometry on a grid that looks like that? Grids are way nicer if they're looking more like this. Like, that's, it's rotated. You might want it to be straight up, but really this is a fine grid to do geometry on. Like, you can see everything really clearly here. you know, even if it's a little wonky like that, that's still kind of okay. But when it gets like that, you know, if it's perfectly straight, that's obviously really bad. But if it's even close, that's also going to be bad in a variety of ways. So we're going to look at that in more depth, but I wanted to go ahead and start taking a look at it now. But yeah, just like to make a concrete point about that, what would you do if I tell you like, okay, here's a point that's, you know, sitting in a certain location with respect to this grid, like you move so many purple vectors plus so many green vectors to get to a particular point. And then here's another one, like what's the distance? Like that seems like a nightmare. You'd really want to just figure out where they sit in the plane. In other words, you'd want to sort of kind of pull things back to a nice square grid like this one and compute distances there using the Pythagorean theorem. So another way to look at that, like that figure up there with the orange points, like this looks pretty nasty. But if I just use gray points, which are, you know, making a 90-degree angle, or rather gray vectors that are making a 90-degree angle with respect to one another, then it's not so bad. You can really see what's going on. I'm going to get a nice square grid as I, you know, kind of alternate which of these two sliders I'm messing with, right? This is reasonable. You know, this is, your eye doesn't have any trouble kind of discerning what's going on here. This doesn't look so dirty. This looks pretty bad. All right, so anyway, bottom line, square grids are better, and we're going to be doing some work later on to figure out how to set up square grids in our linear spaces, even when those spaces are specified in a way that there's no obvious square grid at hand. So for example, to kind of just draw a connection with something we talked about earlier, we had that 100 by 10 matrix that I showed you, and I told you it's secretly three-dimensional. Well, if we could put a cubic grid on that 3D space that all of the rows are sitting close to, then we could describe every point in terms of where it sits in that grid. How many of each of those, they're called basis vectors, each of those vectors that describes that grid, like how many of each one do you need to add to get to a given row? Then that would be great. We could describe every point instead of using 10 dimensions, just using those 3, and we could plot it in 3-dimensional space and start getting some real intuition for the data set. And in fact, we're going to do things like this where you go down from 10 dimensions to lower dimensions so you can visualize, or for other purposes. We'll talk about that quite a bit in Data 1010, and there's some very interesting ideas in that space. But this is kind of the most basic one, which just uses linear structure. Okay, so again, kind of tapping into your existing linear algebra knowledge, I want to ask, what is the linear algebra term for this concept? So the set swept out by a given list of vectors as we consider all possible linear combinations of those vectors. Okay, cool. Looks like the answers are in on that one. So the term that we're looking for here is span. So the span of a list of vectors is the set of all linear combinations you can achieve by varying the weights over R. It's a good idea to think of span maybe a little bit less in terms of this kind of mathematical notation and more in terms of the geometric picture, like that math 3D scene that we looked at earlier, where we're able to vary two vectors, or sorry, able to vary the weights that we were using to combine two vectors and see where the sum is, and we swept out a plane. Like that's how I want you to think of span, the set of all linear combinations. Okay, so just briefly, I want to kind of hear folks' ideas on this. How can you check whether one vector is in the span of some other vectors? So like, let's look at the columns here, these 3 columns of this matrix A. So matrix is just a rectangular grid of numbers. Here, I'm just using it as a container to store these 3 columns. And I'm like, okay, is this column in the span of these 3 columns? Yeah, so exactly. So what we want to do here is solve a system of equations. And specifically, the system of equations we want to solve is this one. So is it the case that there's some value you can multiply by 2, some other value by 0, and some value by 7 to get 24? Well, yes, there are going to be lots of ways we can choose X, Y, and Z to do that. But can we also do it in such a way that the second component also holds? So we're going to be adding the same amount of 7 as we added of 2 up here for this first component. Likewise, it's going to be 8 times Y and 5 times Z, and that's going to have to work out to 14 if it's going to be the case that the particular linear combination with weights X, Y, and Z that we find for the columns of this matrix A actually does work out to be. And the thing is, it's really handy to be able to sort of compactify these simultaneous systems and deal with them in terms of small algebraic expressions. So what we do is we define the product of a matrix and a vector in such a way that this collection of left-hand sides that we get over here, this vector of expressions, is just A times the vector X, Y, Z. And we might abbreviate that even further by writing the collection of weights as a bold-faced X, and then we just write A times X. So again, this matrix up here is A. This vector with sort of unknown components X, Y, and Z is X. And then this whole collection of left-hand sides is A times X. And then this collection of right-hand sides is B. So we're just down to an equation AX equals B. Just to restate this, A times X is the vector you get when you form a linear combination of the columns of A with weights given by the corresponding entries of X. So this is a notion of matrix vector product that is central. I would say it's a great kind of starting point to connect to other notions of the matrix vector product or other ways of thinking about it. I want to point out here that a common gotcha in NumPy is that this matrix vector product is not denoted with an asterisk as most product operations are. It's denoted with an @ sign. And this is true for historical reasons. It's not necessarily great if you don't love it. Welcome to the club. I think pretty much everybody doesn't totally love it, but it used to be that we didn't even have the @ sign. We had to get the Python folks to toss a bone to the scientific computing community and give us a way to use that operator. Otherwise, you had to use an actual method call, and it looks pretty ugly if you have a fairly complex expression. So in any case, we're almost out of time here, but I want to get to the punchline of this particular exercise. The function in NumPy that solves a linear system is called LSTSQ. And we'll talk about why it has that funny name. But first of all, let's read about what it does. So we give it two arguments, A and B, and it tries to figure out how to solve the system A times X equals B. And it returns a solution, so the X that actually solves it, and it also returns how close it got. Like, was it able to really solve the system? If not, how close did it get? That's going to be the second return value that it produces. So let's just see what that looks like. This is a very simple line of code, just LSTSQ of A comma B. And we get some, deprecation warning, whatever. And then it tells us, okay, here's the solution, -2, 1, 4. And it tells us that the residuals, it's 10 to the minus 28. So that's really just round off error. It's telling us that we were able to solve this system exactly, pretty much. So if we want to double check, we have to do this matrix multiplication. So multiply A times the solution that the LSTSQ function came up with, and we check out that this is indeed equal to B. We can subtract B if we want. We get an array of all zeros. So that's terrific. That means that this particular system of equations did have a solution, and the solution was given to us by the NumPy least squares function. Okay, so that's pretty much the end of this lesson. We'll maybe tie up some loose ends here next time and then pick up from there.